All right, everybody. Thanks for joining us for today's CISL seminar. We're pleased to have Dr. Lulin Xue here from RAL. He's going to be providing a seminar today on the NCAR Water Systems Program and its connections with CISL. So thanks for joining us today, and we look forward to your talk.
Okay, thank you, Doug, for the introduction. Can everybody hear me? Okay, so mic is on. So it's really an honor and pleasure to be here. I actually enjoyed the CISL Roadshow a couple of months ago that happened at RAL, that Moha and Doug and a lot of you have been there and giving the very nice overview of CISL. That also prompted a lot of conversation between our lab and you guys in terms of data curation and also modeling support. And it's good that I'm here, return a favor, and try to let people hear to see what's going on from our side in terms of research and also these kind of the computational requirement and data support needs. So I'm very happy to be here. Let me use this thing and see if it works. Okay, so apparently it's a very difficult job to summarize decades of experiences and outcome from that program. I have to rely on a lot of people to come up with this materials, and some specific names are listed because they contribute to the actual contents of the talk, and some basic information about myself on the right-hand side. So I will not read them individually, but I also want to call out, I think, Matt Ravnick. I think he helped us actually make two beautiful animations out of our CONUS 4.4 data set, and one of them will be shown today. And actually, I will also want to make personal notes in terms of my connection to CISL. I actually joined a Image-hosted summer school in 2008. And the topic of the year is like geophysical turbulence. And Andy Maida was one of the main lecturers. And I think during that 3 weeks, I enjoy a lot. One of the projects actually is to use vapor to visualize the DNS result of a wave breaking. So the entropy and all that intricacy of those fluid field. So I had a great time, and John Klein was there at the time. So that was the connection, in my opinion, a long time ago. But after that, we still have a lot kind of communications and connections with CISL too. But today, I would like to use this opportunity to discuss and talk about a little bit about our research, but also connection with you guys. The overarching premise is everything here: water, weather, climate, hydroclimate. How do I say this? Usually, climate can be expressed as an average of long-term weather. And we all know water comes from weather. That's where rain starts, where snow starts, and where they actually fall on the ground. And we look at the hydroclimate is also everything about water. So that's the water cycle that we need to have the weather to convert the vapor into condensate, and then on the ground that we can use. And from the ground, going back to the ocean, and then cycle again. So this is a very complicated system. And that's actually the main kind of target of our water systems program. This is the one-slide summary of our program. And we have been existing for probably 20 years. And it's not a lot of funding, but enough to actually get a lot of these critical research direction moving forward, also facilitating collaborations and community engagement. And we do all kinds of research from global to regional, and also model development and data application. In terms of the products, we kind of really bother you a lot in terms of the volume of the data that we generated. It's starting from early 2000, the Colorado headwaters, to nowadays South America and CONUS 4.4 data. That's all big data set. And we also, along this line, we generate and produce a lot of these modeling tools for the community to tackle different problems. And lastly, we actually cultivated and actually developed a lot of these grassroots groups, such as South America Affinity Group, Mesoamerica Affinity Group, and Human Climate in the United States. So I will briefly introduce those community effort later. And this is actually the beginning of water system program. So that's the paper by Kevin Trembers in 2003. At that time, basically that statement is true. With climate change, precipitation characteristics will change. Its frequency, duration, and all that will be different. But how can we know and how can we study them? Through observations and models. At that time, it's a brand new kind of area. Therefore, the water cycle program was kind of established around 2004, 2005. And the first outcome of that program is this kind of overview paper in 2007. So that's the Journal of Hydrometeorology talking about the global hydrological cycle using observations and climate model to have a basic understanding. So that is probably the first big outcome of the program. And from there, we start to actually get a lot more activities going. Interestingly, at around 2007, 2008, there's another initiative called TIMES, the Institute for Integration of Multidisciplinary System Science. Some of you here are actually remember that. That consists of 3 or 4 programs, including water system program, but also BCOM and also another one for carbon cycle. But that institute did not really last long, and it kind of been converted to ISP. But ISP also didn't survive 2 years. So everything fall back to water systems program after that. So we probably starting from 2009 or 10, that's a stable water system program began. So early on, we had a lot of fearless leaders of this program. Roy Rasmussen is the main leader of the program. Kevin, of course, was the initial idea proposing to study this phenomenon. Igo and Mitch Moncrief. And Changhai Liu, I couldn't find his headshot. That's amazing. Who can actually kind of hide his identity on the current modern era? It's amazing. Kyoko Ikeda, Andres Prime, Fei Chen. I didn't list also Dave Gotches and Wojciech Grabowski. They're also very important contributor to the program. But now, Roy just retired, Kevin retired some time ago, Mitch retired some time ago, Fei moved to Hong Kong, Andres moved to ETH, Kyoko passed away last summer in August. We just had a memorial event this past Monday to celebrate actually her scientific contribution to our field. So many of her work on the water system program have been highlighted. So I just want to use this opportunity to acknowledge her contribution again. Igo is now in Albany. Shanghai is the only one that's still at NCAR. So with this leadership changing, then we have to have a new kind of a leadership right now. So this is the new Water System Program Committee. And as you can see, now we have more lab representation in this committee. I'm really glad that Doug is one of us because he actually started and prompted this conversation and making this event happen. So I really appreciate that. And Holger actually had a good comment after our water system retreat this late April. He said the water system program is probably the only place that we consider the water from all the aspects everywhere from around the earth. So that's the only opportunity you can see it from a big picture, not like specific project only focusing on one problem. So I would take that as a good comment and complementary to our program. And I will also use this slide to highlight our impact and the connection with CISL. So we, as the water system program, we had this different kind of pillars. Research and development as probably one of the fundamental pillars that we anchor on to generate the products and provide these data and tools to the community, and also try to broaden the impact and also enhance collaborations in a much broader sense. And CISL actually helped us in terms of every single component, but more on the product side historically. But moving on, I really think we have a lot more research-related topic to work together. And I think that that CISL sign would be also parallel to the water system program and in the center. Hopefully that's our future. And this is from now on, I will go through these 3 different pillars with different lengths because I think R&D is the main part. So I will spend a little bit more time to talk about what we have done in terms of research. And by looking at this map using the satellite observations, you notice that the most recent 3 decades compared to much earlier time last century, you do notice places around the world, some places gets drying kind of a trend, less precipitation, but some places gets more. So it's a complicated picture, and the impact is very large in terms of our human society. So the very 2 leading questions for our water system program from the beginnings are, how does the precipitation change as climate changes, including all that different characteristics? And can we study these changes for globe, specific regions, and also across different temporal and spatial scales? And in order to answer that question, there are multiple ways. I believe like developing better convection parameterization in the global model, in the Earth system model is one way, but also super parameterization, if you heard of that name, that Wojciech developed, tried to embed another cloud resolving model within the grid of a climate model to resolve these precipitation processes. But water system program also took a very unique way at that time to use these kilometer scale convection permitting model to look at the problem. So what's the advantage of using that very high resolution simulation? So this is the animation showing the topography data from 1 kilometer to 100 kilometers over the Rocky Mountain. As you can easily tell, when the resolution is high, you resolve all these peaks and valleys. But when you move towards the grid spacing of a climate model, the entire mountains just look like a bomb, several bombs. So you lose those details of the terrain impact on precipitation and also hydrology response. And the other advantage of using that kind of a grid spacing is that when you resolve a convection system, when you use this different grid spacing, you actually see this kind of a step improvement when you get to around 4-ish kilometer grid spacing. The whole structure and precipitation distribution sort of like being captured at that scale. So that's 2 advantages of using this approach, that we eliminate the deep cumulus parameterization part to get explicit simulation of strong convection. Therefore, our first trial is trying to see whether that works or not in terms of a relatively smaller area, such as the headwater, Colorado headwater region. So Colorado headwaters are very important to a lot of these different river basins and provides the water sources for a lot of the population. So we use this as a test bed and set up that experiment using multiple grid spacing, and also explore a relatively long-term simulation, 8 years over the whole area continuously. And we also develop, or at least implement, these pseudo-global warming strategy to study the climate change impact of water resources or precipitation processes over that region. And the bottom line kind of a conclusion could be easily identified from these plots. The observation that we use from the snowtail sites that across the entire western states, they are deployed in complex terrain, maybe not the top of the mountain, but at least some reasonable altitude, to collect snow and precipitation through gauges, and also snow from the pillow, the solid phase of snow. So it's a like weighted way of measuring how much snow were on the ground. Funny thing is, when we have to have a clearing to make sure that these precipitation falls into these devices, but sometimes moose and elks can actually walk over that pillow, so you may see some signals from those interruptions. But in general, climatologically, you will have a reasonable representation of the precipitation and snow from these measurements. So when we aggregate that from the whole area that we looked into, we found 6 kilometer-ish resolution give us very close to observation, even though somewhat overestimate, but 2 and 6 are so close, and Snowtail's red is very much along these trend. So that gives us the confidence, okay, as long as we have a grid spacing around 6 over these complex terrain region, we should have a good representation of the total precipitation. So total precipitation and snow would be the first order kind of an important factor for water resources downstream. And this is just a map showing that, yes, only when we get down to 6 or finer, you can resolve those valleys and peaks and where the precipitation concentrate and where they actually can flow later. At 36 kilometer even, we consider as high resolution global kind of grid spacing, you're not able to capture that. So it's just a demonstration of the value. With that successful experience, that we found that 4 kilometers is a sweet spot, that you don't need to spend a huge amount of computing resources using 2 kilometer, but also resolve both the terrain direction and the convection nicely. So the whole water system program start a series of effort after the headwater experience. So we configure we extend our domain to the entire contiguous United States or continental US. And then later we have partners who would like to explore the hydrology impact in Canada. So we further expand our domain to cover the entire Canada as the CONUS 2 experiment. And then South America start to form a group to actually see if the knowledge we learn from US based on the good observation can be translated into places like South America to get reasonable representation of the precipitation and hydrology. And at the same time, Alaska and Hawaii reach out to stakeholders and mention, oh, such a good data set exists for CONUS. How come we don't have it? So we help them actually build another 2 data set for Alaska and Hawaii. So this is a nice summary of our effort. And most recently, another affinity group, Mesoamerica Affinity Group, start to perform impact simulation over this gap that if you look at all the squares, we don't see anything in the middle. That's where we are focusing on from the MAG community. All these circles are indicating the simulation and research directly sponsored by Water System Program, and all the others were through our effort that we found external funding resources, and to collaborate with external collaborator to carry out these research. So let's just move from the Colorado headwaters to the entire CONUS, because that results really give us a really confidence that this might work for the entire CONUS. So even though we don't know, but we want to give it a shot and see what happens. But this time we're simulating 13 years historical period and using the error interim as our initial and boundary conditions. And the same pseudo-global warming approach was applied, that the base state is still the error interim prescribed weather, but the climate warming signal came from the CMIP5 ensemble. It's not an all-member ensemble, but selected member ensemble mean differences, so that we can have a climatological representation of the warming signal added to existing weather. So that is the kind of the definition of pseudo-global warming. I have a slide describing that later. But using this whole CONUS domain to try it out and see what happened. And this is the slide that I mentioned about how to construct your pseudo-global warming approach. So this approach basically simulates the same storm tracks. So the same weather event will be captured in both historical and PGW round. But just say for the same weathers, how they will change in a wetter and warmer environment. So that's how the PGW actually, the information that we can get from this type of simulation. As you can see, all the baseline is the era interim. So that represents the weather or the perturbation on top of climatology. And all signal came from a future period of the mean of the weather of the climate state minus a earlier period of the climate state that give you that warming signal to this weather. And this is one highlight that we found. Similar to the headwater that focusing on the Colorado and surrounding region, over the entire western United States, where the mountains is the main kind of the forcing for precipitation and for water, we noticed that this 9 different subregions over the western United States have really good, our model have really good performance in terms of precipitation simulation. And if you look at their monthly comparison, even not just magnitude, trend, but also variability are very close to observation. And if you look at the time series on this, oops, sorry, I have to go back. For this blow up in terms of precipitation comparison and SWE, snow water equivalent, that is the solid snow on the ground being measured by the pillow. You can see that most of the time our precipitation agree with the snowtail observation very well. The SWE, most of the time our WRF simulation, the red color is lower than the black observed snow water. So it persists in the headwater simulation and in the CONUS 404. And it became a project of the H2S initiative that we want to figure out the reason. So that will be discussed later. But this is also give us the confidence that this configuration really helped us nail down the precipitation in the mountains. But over the plan, we did see some issues. On this very busy plot, the left-hand 3 columns showing you precipitation. From WRF on the left, PRISM, sort of the observation-informed gridded data set. So it has observation kind of information in it, but also have some model component and statistical component there. And the differences between WRF and this data set. And similarly, the other 3 columns indicate the temperature, surface temperature. One thing you notice is that for all these warm season, MAA, JJA, SON, we have a relatively strong dry bias in the plain, in the Midwest, especially summertime, and also quite obvious the warm bias over the similar region. So that feature has been found not just in our simulations, but all kinds of global kind of simulation or regional model. So we noticed that, and we actually make a big effort to improve it later and incorporate that improvement into CONUS 404 to fix that issue. So if we don't try it, we don't know what happened. So we tried it, and we noticed that, okay, yeah, this may work, but may not work that well, and further research improvements to the model are needed. But the highlight in terms of this 13 years data set, we produced so many high impact paper, a lot of Nature climate change paper, a lot of these PNAS and climate dynamic paper. I highlighted 3 of them. One is by Roy's daughter, Kristen, not Roy, even though they share the same last name. So that's by her daughter, Kristen Rasmussen's paper. She found that in the future, we have fewer, stronger precipitation or storms. And that's kind of well known. Like if with global warming, we notice that extreme will become more kind of obvious and become more severe. And to explain that in terms of MCSs or strong convective system, she explored the thin and CAPE relationship. So CAPE is the available energy for you to go up for the air parcel. Thin is the inhibition that you have to overcome to realize that potential energy. And in a historical sense, from this 4 months, we found CAPE won't get too high and thin would not become so big neither. But later, when you get climate change signal add up, you now see a very expanded kind of a 2D distribution of the Cape and seam, which means you may actually have stronger seam for the same level of the Cape and in the future. That gives the answer a kind of an explanation why you suppress some of these slightly weaker convection. But only when you get to much, much higher Cape that the seam is not enough to prevent them, they exploded and generate very, very heavy precipitation. So this kind of a 2D distribution clearly kind of describe that relationship that what we will expect in the future. So that's exactly what we experienced, fewer but stronger storms. And Andreas Prine also have this very nice paper to kind of really separate the precipitation changes into different components of these convective storm. And in the future, the actual rain mass or rain volume we got from these big storms will increase by about this much, 30 to 80%. But the components are coming from both stronger rate, as I mentioned, the stronger the convection gets a stronger precipitation rate, and actually a bigger area. So storm become bigger in the future. More interestingly, the storm may move faster or slower in the future too. So with that kind of the combination, with much heavier rain lasts maybe longer if they move slower and covering a bigger area, of course, we'll get more rain on the ground. So more extreme situation. And this example from Keith actually also is a very great study to look at rain over snow. Because when rains start to fall over the snow, there's no way for them to infiltrate the surface. They're gonna just run off as fresh water. So that is a time when springtime, this happened, this really is the main cause of the flash flooding. So how much more rain on snow event will happen in the future have been explored by this data set. And we actually learned that, yes, more such event will happen with global warming. You're gonna have more rain, but at the same time, in high altitude area, snow will still persist. And then you have more chances to happen, to have this rain over snow event happen. And that's just three examples of what we actually learned from that data set. Also hurricane statistics and all that have been explored as well. And for the CONUS 2 project, we actually want to address just the question I mentioned, the PGW give you the same weather, the same storm track, but just a warmer and wetter future signal. And on top of that, you can now understand the impact of climate change to your storm tracks. But there's another way to do it is to use this, another way of constructing future scenario is to use the weather from the climate simulation and then bias correct that using the base day and then adding up future climate change signal. So this is another strategy that can give us the storm track change impact. So this is the kind of the different strategy for CONUS 2. And because our collaborators and colleagues from Canada would like to use the same data, we extend that to cover almost the entire Canada too. So this is quite a big domain now. And this simulation have just been finished not long ago. So with CONUS 4.4 and all other things going on, this took quite a while. And now we are actively analyzing the data of this round. But this is a more technical slide to show the differences between PGW approach and this more direct downscale from future climate projection approach. So as you know from the CONUS 1, the entire weather is from era entrant, and we can actually split them into the perturbation. Well, that's what we call weather, and the average, we can call it climate. So now is the two components to these weather. And we can construct the historical or the control round the same way by using the perturbation from CCSM. So now your weather is coming from your climate data, climate projection or simulation, and the climate-based data is from the reality or the reanalysis. So using that method, we construct the future differently. And because the weather now is coming from the future CCSM projection, the weather is different than the weather that had been simulated back then for current time. So that will incorporate the impact of storm change. Results, I cannot share it right now. We're analyzing them, so it will come out soon. Hopefully next time when I talk to you guys, we may have something new to update. Okay, so that's CONUS 1, Headwater, CONUS 1 and 2 projects. And the most famous one probably for you guys is the CONUS 4.4, because that really generates tons of data and a lot of activities. And this project is not directly funded by Water Systems Program, but because of all the efforts and experiences that we accumulated, we convinced USGS to pursue this big effort. And this data set, this is the, in general, why we call it 404 is because we generate a data set more than 40 years long with 4-kilometer resolution, and it's hourly data. So it's huge, I have to say. Yeah, we rely on you guys to help us manage the data. The kind of a driving force for USGS to do it is that USGS was tasked by the Congress to do the National Water Availability Assessment. That's a big ask. And they want a very detailed data to actually come up with that report and assessment. So this is the main product of that report. So we're very proud to be part of that. And of course, I can see there were plans to do a lot more other locally refined study of these different basins. As far as I know, we only accomplished DRB, a little bit of the Upper Colorado, and a little bit of the Illinois River Basin, but not much continuation of beyond that. But still, by itself, is a huge effort. And what the data look like, and I would like to show this animation made with the help from our CISL visualization team. Where's my cursor? I just don't know where it is. Oh, it's on the, okay. Sorry, guys. This is a animation using the full 40 plus years of data. But if you're looking at hourly data, that will take you probably tomorrow, you're gonna finish seeing it. So sorry, it won't be the case. We try to show the transition from weather to climate. And now we just look at the hourly data. The blue and then the green and red represent the surface moisture. The whitish is the cloud. And then the blue signal beneath them are the hourly precipitation rates. So with this data set, you can easily look at these hourly variability of everything, but also you can aggregate the data into sub-daily, such as 6-hourly. Most of the climate data, climate simulation data, and reanalysis data is at 6-hourly interval. And you can also aggregate them into daily and see what system or what feature would jump up at the daily kind of the scale. And you may notice tropical depression can easily show up at the daily signal. And when you further smooth it to weekly, you will notice we lose most of those kind of details of the weather system, but more or less, unless you have very huge systems such as Hurricane Allen, it's a Category 5 in 1980. And then most of the time you will see this kind of in-between weather and kind of the climate signal. And we also do that for monthly, seasonal, annual, and decadal. So you can see now, when you see a more like a whitish color, that's getting to the cold season. And warm season, you actually see more precipitation, but less cloud. So that is a climatologically true. And especially when you look at the data till like seasonal data, you will notice winter and spring has more clouds, summer, fall, you get less and less. Very interesting. And precipitation becomes more streaky and patchy, but still you can see some of those heterogeneity. But it gets to annual and decadal, it's almost like climatology. But year by year, you have an interannual change of storm and system. So yeah, and this is a way that you can use the data for. And we're happy that we collaborate with CISL to put this together. And yeah, and let's just say a flavor of how this data look like, just a few 2D fields, and we have the full 3D fields for the community to use. And in order to pull this out, as I mentioned, we accumulated about 1.5 decades of experiences running such model and simulation, that along the way we improved the land surface model and improve the microphysics. Most importantly, in order to address the summer warm and dry bias in the plane, we incorporate a groundwater scheme into the land surface model that in fact actually help a lot to mitigate that issue. So I will show that soon in this slide. So the physics improvement that we made, I only want to highlight two because these are very critical. For the groundwater, in the original NOAA land surface model component, we don't really have a groundwater option. So when the groundwater leaves the bottom of the last kind of soil layer, it just disappears. So you don't have a way to put them as a reservoir to have an opportunity to come back. So with the groundwater, shallow groundwater scheme that we implemented, and we now have a mechanism to store them and to come back later, so that the warm biases after we implement that has been almost totally eliminated. And most importantly is about the storm statistics. Before we implement that groundwater in the CONUS 1 result, the red color indicate model distribution of the frequency of storm in our simulation. So from the wintertime ramping up to spring, we agree with the black observation very well, but get to June and July, everything becomes so dry that we kill most of the storms, that we couldn't capture the second peak of the observed storm frequency. After we implement that groundwater scheme, almost like we're on top of the observation. So it really helped us address that main issue. Now the CONUS 404 data is more useful for this convective storm analysis and study. And another issue is about actually wintertime cold biases, surface temperature cold biases that we found. And by actually changing the snow fraction, kind of the parameter and functionality in the land surface model, we're able to correct that to a reasonable degree, even though some places get more exaggerated in terms of warm biases. But in general, we improved that through this activity. So Water Systems Program not only running model, we actually did a lot of these research in terms of model physics and improvement, and then also iteration of that. I would like to ask how many of you have not seen this animation? Raise your hand. Have not. Great. This is the perfect audience I would like to talk to, because this has been shown so many times that many people already know the answer. But here I will ask. This is a comparison of a simulated and observed cloud brightness temperature. The model is from CONUS 404. The other is from satellite. So which one, in your mind, is from model? Left-hand side model, raise your hand. Okay, if you raise your hand, which means right-hand side, the rest, you guys think the right-hand side is model. Is that right? Please raise your hand. Right-hand side is model. Yeah, we still not get everybody raise their hand because you're hesitating. Which one is right? All right, the left-hand side is from the model, right-hand side from the observation. But I don't blame you because they look almost identical. The bottom line is, at least for this field, if you're studying the brightness temperature property, temporal kind of features, using the data will give you almost the same answer as the observation. So that is the key point I want to make. At least for some of the research topic, this data set is as good as reality. So that's what I want to say. But of course, not every single field is that good. But we have done very thorough validation of the data set against whatever observation we can collect. I can say most of the fields we can use as it is to do reasonable analysis for your research. So that data, good quality of data, really support and expand a lot of other research opportunity. And I won't show any details about this, just tell you what kind of study we have done. Even just within our group, there are communities from universities and from other agencies using the data for all kinds of different kind of topics. But for us, we use the data to help us develop a machine learning-based drought model that can do subseason to seasonal forecasts very accurately. And second is a full water nexus that we use this data to actually explore a new planting strategy for crops and in the future, how we can avoid this reduced harvest and biomass collection. And of course, this whole data set produce all the forcings that are needed by hydrological model. We can now do a full CONUS assessment of these hydrological responses and can play also different experiments using these data set. So one highlight I would like to mention is this using the PGW. We also finished the PGW round, which means the future round. This is one analysis done by Yemu from University of California, Santa Barbara. And what we saw here is a change in extreme MCS exposure density. It's a little bit too complicated, but just thinking about every square that we have population density greater than 50 people per square kilometer experiencing precipitation heavy than 25 millimeter per hour in the future relative to now, what happened? Bad news for the Northeast people. They're gonna experience more than 100% kind of heavy precipitation in the warming and weather future climate. This zone is kind of like where you shift the spatial pattern. Some places see reduction, some places see kind of emergence of these experience. So actually you can see some red dots. That's in the future, these places will experience some extreme precipitation that in the past they haven't. For the cross, that's good news for them because these heavy storms kind of shift over their region to other places, then they may have less opportunity and chances to experience very strong precipitation or hailstorms, such like that. Denver area, sorry, we're experiencing a little bit more in the future. So this is a very nice combination of the model data and the population information and giving a very, I would say, life-related information. So we hope this type of more convergent kind of the research and the work can be done in the future. So I talk a lot about our modeling and simulation effort. That doesn't mean Water Systems Program only do simulation. So we actually have quite big effort in terms of improving our capability to measure snow. Snow is very hard to measure. Thinking about it, when it falls, it's so light, it can be disturbed by the flow easily, and how to design a instrument that can work in whatever environment to collect the right data. So it's very, very hard. So along the time, we have done a lot of these type of observational study. And more recently, there's a field campaign in Gunnison area and also a SOS kind of a snow sublimation project happening over that region. Ethan deployed a terrestrial laser observation for a field of the snow height. So the animation shows the changes of the snow, the height, the snow height through a day. And now everything is like red, which means they're all blowing out. But let's look at it one more time. You will see snow dune moving using this laser observation. Look at that. That's actually the dune moving by the wind. So you can detect that millimeter and centimeter type of differences, even ski tracks. So if you pay attention, there's someone actually ski around the area. You can see the ski track using this laser capability. So if we're able to study at this level in detail and then scale it up in terms of model representation, we can also do a lot of these interesting snow-related water study. And And I also want to highlight other areas of research directly related to hydrology and also related to these convergence in terms of how information were exchanged between the groups and within the model, what variables impact the other variables, and how can we break them down and to have more confidence in terms of response of the simulation, and also developing machine learning hybrid kind of the approach to better predict and forecast stream flows in a smaller region basin scale. So we just say, I don't want to ignore all the other important research topics, just use the opportunity to highlight some, but we do this kind of a research all the time and all over the place. Here we go, the connection. Sorry that I didn't mention that much connection, but here is one slide I stole from your presentation in terms of the history of our supercomputer. Let's just put our different animations up there. And I really remember for the headwaters, we're still using Bluefire at the time. And Yellowstone kind of era start. Then we have the CONUS one on that. And thank you for CISL approving our either ASD or NSA proposals to carry out these big simulations. And Alaska and Hawaii were funded by US Army Corps of Engineers. And we also apply our internal computing resources to finish them. And CONUS 2, a very big one that we already moved to Cheyenne, kind of the stage. And including South America. South America simulations, the resources were actually, the requests were put up by university through the NSF funded project. So that really makes sense that we have these cross community collaboration, leveraging resources. And MAG just start to have some short time simulation using internal resources. The very first run was actually sponsored by Rygen Projects computing resources. So I will highlight that later. And Changhai Liu, the mystery guy here, was named as the guy spent the most computing powers on a lot of these computers. So I think we're proud of him, but he just don't want to show his face. Well, that's okay. I know. It's, maybe that's the reason he doesn't want to know who does he look like. Okay. Yeah, Changhai, I will try to protect you in the future. And tools-wise, that's the data. That's simulation I have done. Now we're moving from the R&D to our products and service kind of section. And this is just one collage of things that the tools that we produce. NOAA MP now become a community model, have a centralized GitHub repo under NCAR. With hydro system, as everyone knows, is also the national water model, but next national water will be slightly different. And then we also have the microphysics scheme being used by operational sector 2. And ICAR is also a very useful tool to do intermediate simulation developed by Ethan. And we also have Andy Newman's the GMAT, a very famous tool and data set being generated for comparison with model with uncertainty estimate. And WEAP is a water management model, an energy planning model. And SHARP, SUMA, or this kind of infrastructure for kind of the combination of tools to actually tackle very different problems. So these are examples, not everything that we have. And data set, okay, beautiful. Most of the data set are on RDA. So that's how we heavily rely on your support. Or even though we still have some camels still on the GDEX, but I believe GDEX will be part of the RDA soon. So you can see CONUS 1 and headwater data, I cannot find it anymore. It's pretty old data, probably have been scrubbed already. But most of the other data sets are well maintained and available through RDA. And we really appreciate you guys' support and help with users' kind of requests and all that. So I'm really happy to see that. And this is a slide to show through the time what the data size look like. I couldn't find it, so I don't know how big that is. KONOS 1 is quite big, actually, with 13 years and a lot of data, but it's historical and PGW together. These two separate states kind of simulation also give a relatively, I would say, moderate size of the data, but because I led this effort, so I actually ran it with 1.5 kilometer, much finer than the rest of the simulations, mostly at 4 kilometer. So the data set size is still not small for 10 years of data. And KONOS 2, quite big, but that's both present and future. So 20 years, that's, in my opinion, still manageable, but getting to KONOS 404, just historical is close to 1 petabyte. That gets to the territory that it's hard for user to actually assess and analyze the data. And SAC data right now, the historical version is on, and we're planning to get the PGW on as well. And this, the PGW of the KONOS 404 are also, together with SAC, is under the planning. And the MAG data, I think Chief here, he recently put it up. It's 2 weeks simulation, but it's an MPAS run. So it has a really large domain and has a slight transition from 15 to 3 kilometer refinement, but it's a cutoff of the global grid, but just focusing on the Mesoamerica region. This is quite big because 2 weeks give you 7 terabyte. We are now running a full year of that region. We hope to reduce the size before we actually talk to you guys, because otherwise it would be a little bit unmanageable. Another connection with CISL is through the Digital Earth Global Hackathon. And thank you, Sam. That's where I met you first. And then I'm glad that KONOS 404 and the SAC data set were actually used at that event. And not just for practicing data analysis, but also for visualization purpose. So I feel, and visualization tutorial. So I feel very happy about that outcome. And finally, let's move to our final section in terms of the community engagement. This is the sign. Actually, I took the picture, so there's no copyright issue. The sign from the Baltimore National Aquarium from last year's AMS or AGU. I even forgot if it's AGU or AMS. But this is beautiful. Water connects all living things. But in my opinion, water connects everything. So that's a water system program, connects a lot of other things, including internal base fund programs such as STEP, Inform, SPET, and all other very different topics that touch upon water. Basically, almost all the important questions that we study have a component of water. Even wildfire, that's still, if you don't have a dry condition, you will not have that situation. So it's still a water problem. So we are happy and be sit like up in front in the center to glue and connect to all the different efforts. So for the SAG community, we established that in 2009, really grassroots, and we have all these different members joining us through the years. Now we have more than 100 participants from more than 10 countries, probably getting to 20 right nowadays. And the key question is the simulation. The historical simulation will allow the community to validate, model detailed hydroclimate features over the entire continent, and hopefully to study the future impact of that. We also have our CSM, or variable resolution CSM simulation configured over the same region. So Julio and Patrick are part of that effort as well, try to intercompare with our work result. And recently, this group took a kind of a strategic brainstorm activity, and I believe the first topic is more on the future opportunity, in existing opportunities for the next 5 years. The next one about training and capacity building is really highly relevant to data access, analysis, decolonization of the data access, and tools. And this is perfect kind of topic for CISL to be engaged. And our next near-term plan is try to do a land surface change, smaller scale simulation, and to assess how these land surface changes impact the hydrology system. For the MAG, I have to accelerate a little bit because I'm close to the end of the time, but We established MAG community much later, so it's like May 2023, and the year after that, we tried to get the community together, collect the research interests and the inputs before we pulled out whatever simulation effort. And then starting from last year, spring, summer, we kind of march along until now we are in good shape, try to do some 1 year round over that region too. So Rajin from Tim, from John, actually graciously gave us that computing resources for the 2 weeks run. So we already generate that data and have some nice MPAS simulated precipitation compared to the iMerge, even though our track is a little bit off in terms of the heavy precipitation area, but in general, we have really good representation of the precipitation using this tool. So thank you, CISL, for the support, but also we would like to talk to you more in terms of how to make MPAS data more accessible and more user-friendly. That even a beast for myself. So finally, H2S. H2S now is actually a real project, a real GWAX project in response to that weak water problems. So it's now have 4 different kind of the prompts, and now we are trying to identify resources to establish our kind of the governance and try to make sure things happen smoothly. But that theme of research or working groups spread out to very different questions. And the very first project that we had is a SWE bias issue that I mentioned. All our model simulation have very good agreement in terms of precipitation. That's the top line. But we always underestimate the solid snow on the ground. It persists throughout 20 years. So we now have a very concentrated effort. The effort comes to fruition soon. So we'll have a paper out soon to reveal the problem. And this is the timeline that we start from 2019 also. It's kind of incubated through the Water System Program, and the other 3 areas that we try to focus, including observation, including DA component, and conversion with human and digital Earth. So that's where CISL play a very important role there. Okay, the very last 1 minute, I would just moving forward from this very simple or symbolic representation of a hydrological cycle to a new version 15 years later. That this is a USGS version. We notice a lot more human components in the water system that needs to be accounted for. Right now, we haven't really have a clear handle on that, but moving forward, we would like to at least tackle that human component in the system. Also, some interesting overestimation of precipitation at mountains that have been found by both climate model and our regional model. And we will connect to SBAT through almost all the initiatives and connection to Inform. That these DA part is quite important because we want to build the best data for training. And then later on, the machine learning model will be our main tool to do all kinds of different research and downscaling. Of course, we continue to support SAG, MAG, MPAS as well, collaborations with CISL on the AI machine learning part from DJ's group, but also from the data curation part, data comparison, data compression and visualization and more. So I would leave the very last slide as a teaser that recently was collaboration with DJ and Credits group that we already start to use the CONUS 4 data to train a machine learning model to generate this high resolution data close to CONUS 404. So using the Error 5 as input. So we are getting close to have some working version of the AI model that's useful. So I'll stop here and thank you.